So hi everyone, my name is Nicolas Fleury. I'm a technical architect at Ubisoft Montreal. It's an honor to be with you today. Ubisoft Montreal is known for its huge AAA games, open world games like Assassin's Creed, Watch Dogs, Far Cry, important games like Rainbow Six, Splinter Cell, Prince of Persia. I've been at Ubisoft Montreal for 8 years now, 11 years in the game industry. Before I was working in other industries, but still in C++. But coming in the game industry will change the way I see C++. And I want to share part of that experience with you today. This is a talk where I will cover a bunch of different things. Maybe I will repeat a few points from the Mike Acton talk earlier, but my way. So first I will discuss the situation at Ubisoft Montreal. Then I will talk about what we do to improve compilation time and iteration time in C++. Then I will discuss a few performance issues. And finally, we will conclude with some debugging tricks and tips. And please keep your questions for the end of the talk. So first, the situation. Ubisoft Montreal, it is, as far as I know, the biggest video game studio in the world, slowly reaching 3,000 employees. And we're working on big games, up to 1,000 employees worldwide at the end of a project, with up to 400 in Montreal. And the technology group, mainly in Montreal, has 300 developers, approximately. And it's pretty much a Windows-centric development environment. Even if we're doing multi-platform development, visual game consoles, they come with Visual Studio integration. So maybe a few points on a few slides might be Windows-specific, but not much. And working on big games, big code base, biggest one, Assassin's Creed Unity, which will be released soon. I could count over 6 million C# lines of code in the code base made by different Assassin's Creed teams over the years. That is in the code base, actually. 9 million more C++ size of code that are from outside the project, so that can be technology group code, that can be code from external partners. And I could count 5 million C# lines of code as well. If we look at Rainbow Six Siege, the game I am working on, if I count only the code that we are compiling and linking together in the same executable, I can count 3.5 million C++ lines of code made by the Rainbow Six team, and 4.5 million C++ lines of code from the technology group. Even the technology group code, typically we compile it on developer machine because we want to be able to tweak that code and debug it. And I think overall we still manage to have a good compilation time. Compiling and linking all that together, it takes 3 minutes to 5 minutes, depending on the targets. I will discuss more about that soon. The code structure of the engine, the game itself, I will describe it as an inverted pyramid. We have multiple layers, and they introduce new external libraries. At the bottom, we have the core of the engine, so mathematics, object model, very simple stuff that is used across all the layers. Then we have the graphic layer, which is responsible for rendering, where performance is extremely important. And then over that, what I would call the engine services, so physics, sound, animation, services that are used then by the last layer, the gameplay layer, which contains code that is specific to the gameplay of the game. We have senior programmers working in all of these layers, but junior programmers, they tend to often end up in the gameplay layer. So it's really important for people working on lower layers to provide an API that is as less error-prone as possible to the higher layers. And not only not error-prone when it comes to stability, but also when it comes to performance. And sometimes if we have to choose between the two, we might choose performance. Container might take the most performant approach by default, but if you want something else, you need to specify it explicitly. And we don't consider C++ to be the most productive language in the world. We use it because we want performance. When we don't care about it, we tend to instead use C#. So the editor that is used to make the content of the game is made in C#, and it is embedding windows that are from the engine in C++. And it is communicating with the other process through TCP/IP. And of course, when we need performance, sometimes we migrate code from C# to the engine side in C++. There's stuff we don't use. from C++. We don't use runtime type information. We have our own reflection system, our own object model. We even ship the game with our reflection system. So we have data-driven systems like FX systems that can edit properties of objects through complex property paths. And we want to control the exact memory overhead of this system. We don't want to ship with the game with class names or property names. That will be a waste of memory, and that will help hackers uselessly. We don't use exception handling. In the past, it had a runtime cost on some platforms as high as 10%. So that was clearly a no-go. But even today, it still has a compile time cost. And anyway, there's no return on investment for us to make our code exception safe. We have utilities to register call stacks where there's stuff to fix. And we even use a static analysis tool like code coverity that can tell you, this function, 8 times of 10, you're looking at the return code, but here and here, you're not making a mistake. We don't use the STL containers in the engine, but we do use the STL algorithms with other containers respecting the STL interface. We don't use std vector because our array class has more features, especially debug features. And for the other containers, there are alternatives with better performance. Often these alternatives, they will come with some restrictions. For example, a map container could say only supporting key and values that are value types that don't have constructors. In our case, not only we're fine with these restrictions, but we see them as features. I don't want my programmers to make a map with keys or values with constructors. And we never ship a game with a map with a string as a key. This is just not the way we work. And the last one might sound controversial, but we have no boost included in the engine. Sometimes they appear in the past, they were removed for completion time reasons. We have much better completion now than back then, so maybe they will come back in the future. I don't know. Iteration time. So as I said, I think we have a good completion time considering the huge code size we have. The first tool I want to mention is a tool called FastBuild. FastBuild is not bringing anything that much new to the table to us, but it is containing a bunch of utilities and tools that we're using before as solutions for completion time. So what is FastBuild? For us, it's replacing MSBuild for C++. So it's really a makefile tool like BoostJam or gmake. It's open source, and it's made by Frantin, who is working at Ubisoft Montreal today. So compared to MSBuild, for us, it means smarter DLL dependencies, since we can compile CPP files of DLL without waiting for the dependencies of the DLL itself. Better CPU usage according to our numbers. And it has support for distribution and caching. Sorry. So what we do is that it's like Incredible basically. So what we do is that we run FastBuild workers on every developer machine, and every developer is contributing the compilation of others with as much as half of his cores if its machine is idle. What's interesting is that before I said, 3 to 5 minutes, depending on targets. 5 minutes is actually without distribution on Rainbow Six. An Assassin's Creed building without distribution is a bit slower. But the serious thing is that with distribution, we seem to compile pretty much every project at Ubisoft Montreal in 3 minutes. There's a kind of a critical path that we have that is harder to make, it's harder to go slower, faster than that. And FastBuild has also support for caching. So the way FastBuild is distributing compilation is by preprocessing locally the file to remove dependencies of all the includes, and then send it to other machines. So it can make an MD5 of that preprocessed file and look on a cache on the network. The result was done already by somebody else. So what we do is that build machines on the build farm, they will update the cache because there's overhead, so we only do it on build machines. And programmers, they typically don't sync the head of the code always. They instead go through a tool that will sync the last change list that was successfully compiled on build machines. So it means that the cache is up to date. So the first time a programmer will sync, the compilation will be extremely fast because typically programmers, they work on very high layers. So a big part of the code is, they will get it already compiled for almost free. And lastly, FastBuild supports Unity builds built in. We've been using Unity builds at Ubisoft Montreal for over 10 years. We call them the blobs at Ubisoft Montreal. So if you don't know the concept, it's the concept of having special CPP files that will basically include a big number of CPP files and compile that Unity CPP file instead. Overall, it will compile faster, it will also link faster, might inline a few more functions as well. So it has consequences. It means your file scopes, you need to have unique names. If you make defines in CPP files, you must not forget to undef them because that can affect another CPP file in the same Unity. But most importantly, it means that you need to maintain still a compilation without Unity builds because you want every CPP file to have all the included needs. And people will also complain when using Unity builds that when I modify a CPP file, then I need to recompile the entire Unity. In our case, it hasn't been true, but only the first time we modify a file. So what we had before is a special Unity, a work Unity, and we'll edit a file, it will remove it from that Unity and put it in the work Unity. So that way you will iterate over your work Unity. I've never done it, but you could even do that in parallel as you first edit the file in Visual Studio, directly launch the compilation of the Unity-change. But since FastBuild is creating the Unity builds on the fly as it is compiling, it doesn't even need that step. You can just remove from Unity builds the CPP file you are working on and you just iterate over them directly. There's other stuff we do as well. We use precompilators like a lot of people. Some people, they think they are competing with Unity builds, but for my numbers, they are completing each other. Where we don't use precompilators is in some distribution patterns, depending on platforms. Sometimes they are not worth it on other machines to use. But locally, for us, it's a big gain. Oops, sorry. There's one Microsoft compiler option that I think is really interesting for debug builds. The option is called OB1, not to confuse with the Star Wars character. What the OB1 is doing is minimal inlining. So it will inline simple functions from other files. So it might sound weird at first to have a debug target where some functions are inline, but I've been working with that for over 5 years now, and I don't want to go back. The reason is that my debug target is not much faster, and since it's a video game, it's appreciable. And also, it will link faster because there's a big bunch of symbols that don't need to be in object files anymore. This one is really important when people have bad completion time. Is often because of templates. So we try to make template classes derive from non-template based classes. The idea is that template code should end up inlined by your compiler. Otherwise, maybe you should write your template code differently. So if I take an example, in Assassin's Creed 1 at first was not done. So we had an array class, the entire code was there. And then in every translation unit, we recompile always the exact same array types. Even if we use Unity builds, we still have maybe 300 of them in our code base. So what we did instead is that we changed the class to move inside a non-template based class as much code as possible. In some cases, even a CPP file to make sure it's not in line. Yeah, and then in the templated code, we keep simple functions that will end up in line. We also use a lot of generated code. We have our own interface description language for our object model. So basically, next to most header file and CPP file in the engine, we have another file that is the interface description file. And there we declare classes, structures, enums, and some of their properties and functions. And this file is responsible of code regions inside the corresponding header file and CPP files. So for example, in a header file, you will have a class, and as the bracket is opening, you have a code region. And you can still, the programmer can still write his own members and own functions outside the code region. But the code region itself is completely handled by a tool that we run very quickly at the beginning of every compilation. And this tool is allowing us to do interesting. We can avoid a lot of metaprogramming in the CPP files. So for example, the serialization function, they know exactly all the properties were declared inside the interface description file. In a header file, we can sort members to minimize padding between them to save memory. We can generate IDs as CRCs of names, all of that directly inside the tool. So basically, we have created another file with another timestamp that will affect the generated code, so that way we can then speed up the C++ compilation alone. And we also have our own programming language that actually, it looks very much like C++. It's actually generating C++ under the hood. The reason we did that language is because we wanted to have edit and continue working on 64-bit platforms for gameplay programmers. We even went further by making sure that edit and continue is working even in multiplayer sessions, propagating code to all players. We even wanted to be able to remove and add virtual functions. So when it comes to the virtual functions implementation, it's not using the C++ virtual functions. We have our own table so that we can patch function pointers at runtime more easily. And since generating C++, we benefit from inlining and all the performance from C++. And we used preprocessor tricks like dash line and all of that to specify the original file line. So we support the C++ debugger completely naturally, since for the debugger, it's like it's C++ anyway. And we have developed some tools over the years to help us speed up and improve our code. One tool to mention is an object analyzer. So the idea is to give you the size of a symbol, but by making the total of its size across all the translation units. So you might see functions that are in header files but should not be there because they are just too big. But more likely what you will see are templates. The array class I've mentioned earlier about on Assassin's Creed. Before doing that change of splitting the class in two pieces, on Assassin's Creed 1, that class, before that change, was taking almost 80% of object files of all the game. Imagine you have multiple millions lines of code engine, and you have a single template class taking almost 80% of object files. Still today, with the changes we did in debug, we have some functions that don't end up in line because of debug checks that we have in them. And still, the array class is taking 15% of object files in debug target. We also made our tool to remove useless includes and add forward declarations. I won't talk about it much because we realized recently that Google's include what you use is actually a better tool. It needs less configuration to achieve the same thing, so just use that thing instead. When it comes to performance, it's well known that we care about performance in the game industry. So performance is really important for us. The last console generation, it lasted for 8 years. So you can imagine that we need to be able to always make more with the same. There's a 90-10 principle occurring. Pretty much 90% of the time is wasted in 10% of the code. So people working on that 10% pretty much have a different mindset than people working on the rest of the code. That mindset is pretty much similar to what we heard from Mike Acton earlier today. And the way an engine is made, it has a frame rate. So it's a big part of the code is being stressed continuously. So it's not like a desktop application that is event-driven and it's not running that much code. So yeah, typically a game will run at 30 frames per second, so 30 FPS. In case of games like Rainbow Six Siege, it's even 60 FPS. What happens is that when shipping a game, maybe months before shipping a game, especially single-player games, your game might be running at 20 FPS or 22 FPS. But you want to ship a game at 30 FPS, and you don't want to cut stuff that people have put a lot of effort in. So what happens is that a lot of people, a lot of talented programmers, they are dedicated to just optimize stuff the last months of a game. I've been extremely impressed in the last 8 years seeing people optimizing code that was technically have been already optimized by multiple other talented people, and they succeed. One way of doing that is by understanding the hardware. So I want to give a quick example, very simple. I have a structure. It's basically an array of integers with a bunch of different values. Then I make a huge array. The exact size doesn't matter. In that case, it's 1 meg of objects from that type. And I have two different pieces of code doing the exact same thing. They are just calculating the total of all the values. So I don't know if you expect these two to run the same speed, which one you expect to run at the same speed. I've seen a lot of tags this week that assume that you know the answer to this. So if it's not your case, let me explain it. So if I run this on my PC, the second example is running 8 times faster. So why is that? Programmers, they understand there's a huge difference between the RAM and the hard drive. They don't have access to two of them anyway the same way. Hard drive is bigger, it's slower. But the CPU and its registers is not accessing your 8 gigs or 32 gigs of RAM directly. It is going through on the processor through multiple layers of cache. The exact number of caches, it depends on the hardware, but there are common stuff. The L1 cache will be specific to the core, while the last level cache, in that case the L3 cache, will be shared across all the cores. So suppose I imagine here some fictional hardware made of 6 cores. The L1 cache is specific to the core, and then I decide that the L2 cache will be shared across pairs of cores. And finally, I'll have the L3 that is shared across all the cores, and then the memory. So when a core is accessing memory address, it first look if on the road it will look if it's in the L1 cache. The caches are caching cache lines. So for example, the L1 cache could be 64K big and with cache lines of 64 bytes. So it means I have 1,000 pieces from the memory, 64 bytes big, aligned at 64 bytes. These pieces can be from all around the place in the main memory. So it will look if the address, the memory it's accessing, if it's part of a cache. If not, you have L1 cache miss, L2 is check. If it's not there, L2 cache miss. If not, then you have L3 cache miss, and the main memory will be accessed. So the L3 cache miss in that case is the worst case, because then you need to pay the price of the speed of the main memory. Since every of the layers, the same rules are playing, the further you get from the core, the bigger they are, but the slower they are. There's a lot of things here to talk about, interesting stuff, how much all of this can be done in parallel, all the processors making sure all the L1 are coherent, but I won't. I think as a C++ programmer, what you need to understand is that the less you access a memory address, the more likely you are to, the more likely you are to pay a high cost. If you work with huge data, and you don't work properly, you are also likely to have a big performance hit. Also, typically the way the L1 cache would be handled, if a core is writing to its L1 cache, it will have exclusivity to the cache line that it is writing to, which means that if 2 cores are writing to the exact same cache line, even if they are not writing the same bytes, you will have a performance hit. One example earlier this week on an Upstarter's talk, where you have a multi-threaded container and aligning the node on the cache line size was improving performance greatly, because that way you could not have 2 nodes in the same cache line. So if you come back to the example that was running faster, it is accessing memory in a completely sequential way. This is the best because even modern processors today, they can detect such patterns and even prefetch the cache in advance to minimize cache misses. But if we switch these 2 for loops, then we're accessing memory in a completely different way. We're first getting the first element of every object, and then we start back and get the second element of every object. So if I'm on this fictional hardware, I have cache line of 64 bytes. The size of a integer is 4, divide 64 by 4, it makes 16. I could expect this to run 16 times slower. Another example, very simple, I have a structure with an integer member, and I have a function taking a bunch of values. It will just update the member with the total of the values. And I have 2 simple implementations. The first one is very intuitive. I'm just iterating on the values and incrementing the member. And the second one is using a variable on the stack. You expect these 2 to run at the same speed. If I make the test on my PC with the Microsoft compiler and O2 optimizations, And the second one is running 12 times faster. There are two things happening here. This is dependent on hardware, and this is dependent on the compiler itself as well. So what happens is that in the first example, your compiler is very likely to decide that what you're doing inside the for loop is read from memory, make the calculation, and then write back to memory. Very quickly, in the next iteration, you're reading back from the same memory. So there's a read after write opening on the processor. Processors will make sure that read after writes are as fast as possible. But the point is that you cannot expect this kind of operation to be as fast as just working with the registers that are on the same core. And this is what the second example is doing. As far as I know, compilers could decide to transform the first example into the second example. But obviously, they are not, and I've tested with Clang as well. When it comes to singletons, I don't know if you have singletons inside your different code bases. I can tell you that with the huge code base we typically have at Ubisoft, we have a lot of singletons, a lot of classes with name ending with manager because we lack imagination, especially when it comes to singleton names. We don't want to create them on the fly. We want them to construct them in the deterministic order. We want to destroy them as well to have dynastic after like a release. So what we do is that we use a property of C++, very simple, that constructors of members are called in the order declaration and destructors in the reverse order. So every library has a special structure that we call singleton story, where we declare our singletons in their order of dependency. So how to implement such a singleton? One way of doing it is just have a static pointer and set it in the constructor. But what happens if this singleton is accessed thousands of times every frame in very different contexts? What happens is that you get something that is actually less performant than just using global object. And I couldn't measure the difference on an Xbox 360. The reason is that the global object, you will access directly the memory address of the object itself. While here, the global object is actually the static pointer, so you have an indirection. The problem is not CPU instructions to just dereference. The problem is the cache miss that could occur. So one solution is just to use global objects instead and call maybe their initialize and shutdown functions inside the singleton story. Another solution we propose that is available in our engine is a class called GlobalSingleton. So what it's doing is that it has a static buffer that has the same size and the same alignment as the type you are passing. And the scope nested class under the hood, this constructor will make a place meet new inside the buffer, and the destructor will do the opposite, call the destructor. So then getting the instance is just casting the address of the buffer as a pointer to the singleton type. So in the end, you get a singleton that has the same performance as a global object, but with control construction and destruction. I have talked about data cache miss, but there's code cache miss as well. Maybe when you started programming a long time ago, you were writing, you had a bunch of shapes of different types, you were writing an ugly switch case like on the right. Then you realize, no, this is not the way I should work. I should make a shape abstract base class and have an abstract draw function in it, and then every shape type will implement the draw function. Then you iterate over a huge array of shapes, and then you call the draw function on every shape. What's happening under the hood? The object pointer will be dereferenced, probably to get the first 8 bytes of your object to get the vtable pointer. You might have a cache miss, but maybe it's not such a big deal because probably the draw function will access members in the same cache line. Then it needs to access the table itself. If you have a lot of shape types, good chance you have a data cache miss here. Then you're only interested in a single function inside that table. You get the function pointer, and then you go to where the code is. Again, hard to predict that you were needing that. Good chance you have a code cache miss as well, because these two are multiplied the number of types you have. A quick fix is to at least sort your shapes by type. That way you will get these cache misses only as you meet a new type. But what I'm saying is not to not use virtual functions, it's just that people working in that 10% of code, will avoid the pattern at left. They will typically instead aim for data-driven programming. The idea is to remove abstractions. Don't iterate over pointers of shapes. Iterate over shapes. And put the shapes of the same type together. So you iterate over the single shape, and then you also avoid code cache miss because you're running code exactly for that type. And since you iterate over shapes themselves, you iterate over them in the order they are in memory, which will make the best performance possible. The processor can help you to prefetch more easily. And to be honest, when on video game consoles, if we need to prefetch manually to help the compiler, we do it. Don't do that on PC, that can slow down things. But on a fixed hardware like consoles, we even prefetch memory ourselves. I want to come back to an example I've shown earlier with the array class when we divide the class inside in two classes. So what we did is take template code that was not being end up in line and put it instead in a base class and make that code a bit more generic. So basically, that code would have slightly more instructions. You know, we will pass probably a size of type, maybe an alignment of type. So does it run slower? I think it might even run faster, and I want to at least talk about that. In the case on the left, if there's a constructor or something and that type, and I'm instantiated my array class with 3,000 types, it means I have 3,000 functions in memory. If there's no constructor or something that's so type specific, probably maybe with the different size of types, probably I will have maybe 30 functions in memory. But you can understand that you increase the chances of code cache miss with the example on the left. My point is just that templates, especially templates that don't end up in line by the compiler, they might give you the illusion that you get something at runtime, but you might not. Another thing we do to improve performance is trying to avoid the heap. The heap is heavy. I always find it funny when I see people writing containers trying to make sure everything is in line, while the way they use allocations is taking more time than the rest of the container combined. The heap is global, so you can allocate in a thread, deallocate in another thread. So, and you pay a price for that. And in video games where we allocate so much every frame, we can have issues with fragmentation. Fragmentation is really simple. You still have space inside your allocator, but it will still go out of memory because you're asking a buffer that is bigger than any of these small spaces. Something that was done on Assassin's Creed 1, and we're still doing today, then when we have an array on the stack like this, in our case it's like our STD vector, we look at what is the typical size. What size is big enough for 95% of the time. Then we replace that by a class we call in-place array. So it's not like a STD array, it's more like an hybrid between STD array and STD vector. So it will use the static buffer if the size is, in that case, 8 or smaller. So it will use the stack, so you will save a lot of CPU, everybody is happy. And if it's bigger, then it will use the heap. So on Prince of Persia, I started to do the same changes as on Assassin's Creed. They were giving good results, but when it came to memory fragmentation, I was still, once in a while, in that case, allocating. I was wondering, is there a way to do that more automatically? And then we found patterns on different platforms to know if a pointer is on the stack. On Xbox 360 and PlayStation 3, it was as simple as a mask. It was undocumented, but for us, that was good enough. So what we did is that we changed the array allocator to look if the disk pointer is on the stack. And if it is, we use what we call a frame allocator. So it's just a different allocator that is asserted to be empty at the end of every frame. Since it's empty at the end of every frame, there's absolutely no fragmentation with everything going through that allocator. It's really cool because this is even working for arrays that are members inside objects on the stack. In doing that change at that time on Prince of Persia, it removed all the remaining issues we had with fragmentation. Could play the game for 40 hours, and no such problem. When it comes to debugging, we have our own challenges as well. We have a huge multi-threaded code base. You can imagine, same code base with over sometimes 100 programmers working at the same time in it. As a consequence, we have bugs that are only reproducible in optimized targets, since different tasks are running at so much different speeds. We want to avoid recompiling for debug options. We want to debug issues as they are occurring. The debug targets, they must be fast to be usable because a game running at 2 FPS, it's no more a game. This is unplayable. A consequence for the debug targets, there's a bunch of stuff we disable. This is all Microsoft stuff on this slide. Debug iterators from STL. I said we're not using STL, but we're using third parties using them, and we're using it's using our tools as well. The Visual Studio Debug Heap we disable, and we disable the Windows fault tolerant heap as well through the registry. The last one is something Windows is doing when the application is crashing too often. It will just assign a different heap to it, but prefer to fix the crashes than have something running 10 times slower. And all programmers, they need to be able to debug release code. We have a one-day course that is very popular in Ubisoft Montreal, where programmers, they typically learn to get back the disk pointer from the code, the assembly, and the registers. Here we can see a screenshot of a Visual Studio extension we have that is adding information so that people understand code, the assembly better as well. So I won't give the course, but I can at least share one tip with registers. So suppose on your PC you end up with a call stack like this that's completely empty. If you don't know what to do, you're pretty much screwed because you have absolutely no idea what just happened. What happened is that your restriction pointer register is now corrupted. And what you can do is just look at the different registers, and typically there's one with a value good enough to debug. And just try them very quickly, and as you press enter, you will see your call stack resurrect from the dead. When it comes to memory allocations, I said we try to avoid them, but the reality is that we're doing a lot of them. So much that we don't debug them individually. So what we do instead is that we use something we call memory tagging. So every memory allocation we do, we pass a string that will be used to tag that allocation. We even pass a parent pointer, but the parent pointer is not used for ownership at all. This is behaving like any C++ new. The parent pointer is used to make a path with the tags. So like paths on a file system. So the reason we work that way is that it has a very low memory footprint. It's not an issue on old gen consoles. Because we just need to keep an atomic count for every path, and that's it. So for example, on Prince of Persia, I had a tester playing the game for over 20 hours on multiple days. And and then he will come back at the central hub, and he will make regularly a memory dump. So then it was really easy for me. I will just make a difference between these dumps and see which memory tags were leaking. Then I will break in the debugger on these tags and just fix the code accordingly. The way I will break inside the code is by using something we call the breaks. It's very simple. It's just that a bunch of our singleton and managers, they have a global object which just is just a structure with a bunch of values that we can set to trigger breakpoints in debugger. So they are like conditional breakpoints from the debugger, but with two advantages. They are much faster. Conditional breakpoint from the debugger, if you're running through the code where you have put it, that will be extremely slow. But here they are compiled inside the code. And you can set them, you can pause the debugger and set them at runtime, or you can set them at compile time. And also they are permanent. So if a new developer arrives on the project, we have a master class with a member for all of these breaks classes. And so we can browse through all the breaks available inside the engine. On this screenshot, we can even see that we have another master class. And we can even actually browse through all the singletons, for example, all the singleton starters. When it comes to memory corruption, as I said before, you can have as much as 100 programmers working in the same code base. A lot of people using the same heap. So you can understand that another programmer can make your code look bad. So what happens is that when we have a memory address where we suspect there's been a memory corruption, we pose a debugger and we have a function called debug memory. We can pass that address. But what it will do is tell you which allocation was done in the past close to that address. Because often what happens is that someone is writing to an object that is actually now deleted. So this is finding things after the fact, but often this is good enough. What we like to do in the future is not even run code inside the process, but instead have a Visual Studio add-in that is getting the memory and then cast it in C# and make the exact same thing. So we have another approach as well. We have an allocator that when you allocate, it will allocate a complete page for allocation and put the allocation at the end of the page. And the next page is allocated as read-only. So that way, if you write past an allocation, it will break directly in the debugger. It's a crash. You are trying to write inside the read-only page. And when we deallocate this object, we'll keep the page as read-only for some time. So again, if someone is writing to an object that has been deleted, it will break in the debugger directly. It will be a crash. So this is cool because now we are finding the memory corruption exactly as they occur with the guilty code. Philo, sorry? Yeah. Yeah, of course we have asserts inside the array class. But suppose I just have a pointer to an object, I could cast it in on the wrong type and then access past the address. Oh yeah, okay, that will work as well, yeah. Yeah, so, but the problem with this is actually that's taking a lot of CPU time to allocate all these pages. So we need to use it with specific allocation on maybe specific size depending on what the problem was. I was waiting for questions at the end, but anyway, that's on the next slide anyway, so. Not the entire game. Not the entire game, no. But I think I've done it on a Just Dance project, but yeah, someone tried to do it on Assassin's Creed. There's no way. But if it was only a memory problem, we will not care. We say, okay, we have a machine with whatever RAM is necessary, but no, it's more a CPU problem actually. Okay. Yeah. So that's it. Before finishing the talk, I want to mention the first reference link. It's a talk from Game Developer Conference in 2003 from Mr. Erickson from Sony. If you're interested in memory utilization, it's really interesting. So that's it. Yes, we have time for some more questions.
Hi, can you tell us briefly a little bit about what kind of concurrency primitives you guys use? Is it kind of a set number of threads? Is it thread pools?
Actually, the next talk of my friend Josh Pressing is about a bit of that. I want to spoil him. He's really answering that question in a 1 hour talk. So you will have your answer in like half an hour.
Thanks.
Do you use any other debuggers like WinDBG for some of those problematic crash cases, or do you just use the default
we use
debugger?
the Sony offer, and then it's Visual Studio, and that's it.
Yeah, I wanted to ask if you guys have used, if you use any other memory debugging tools, such as like address sanitizer or anything like this, or if this is completely infeasible with video games.
By me, I have not. I don't know if people have tried. Yeah, we tend to have a lot of custom solutions. Oh, interesting.
Lots of familiar stuff. So, just out of curiosity, feature selection. You know, when we're talking about a game this size, games this size, teams this size, games, different types of games. Do you have any systems for feature selection between them? Anything that's actually managed, or is it pretty monolithic?
Sorry, can you repeat the question?
Do you have any systems? Ubisoft have any system for feature selection between the games? Like, are you cutting out parts of?
Oh yeah, okay, yeah.
Yeah. So is there something how you manage?
Yeah.
it?
Sorry. So we have you have possibilities of choosing features for a game. At Ubisoft Montreal is extremely organic. Every project is branching from whatever project, so it's pure chaos. But it works. That's actually how I think we are able to be 3000 because we are extremely bottom up. So we work the same way as a 300 studio in some way. But yeah, so yeah, every project is branching, and then they will just remove stuff like crazy that they don't want. And if the sequel needs again to have an ocean or something, boats, oh, we need to put it back. So yeah, we're definitely we're not working in a modular way to remove stuff and add stuff. Maybe it's possible, but the real life situation is that we're not doing that at all. It's pure branching and very organic, natural section, good ideas that will finally come from project. What we've seen over the years is that having people moving from project to other projects, as they get smaller and bigger as they ship, it's really helping to propagate good ideas. People will say, hey, I was using that on Watch Dogs. So yeah, that will say that it's very organic. That's the answer.
How much of a performance boost do you get out of having a Unity build versus relying on link time code generation?
So yeah, how much performance we get at runtime from Unity builds? I don't know. Maybe the Assassin's Creed one, they will have a good idea. At that time, they were maintaining both builds. On Rainbow Six, we only compile without Unity builds just to make sure they have includes. We don't even link that target anymore. So I really don't know, but I know it's inlining a few more functions since often you have functions that are good candidates for inlining in CPP files. But yeah, that's it. More questions? Thanks for it. Oh, sorry.
Your code base predates the C++11 standard. Could you talk about what any C++11 features that you've added since the standard came out?
Yeah, but I had some slides about, so the question is about C++11 usage. I had some slides at first regarding some features we use from C++11. I removed them because they were not fitting in any of the 3 sections, really. For us, C++ is pretty much what the different compilers are offering. With the new generation of consoles, it's much better than in the past since Sony made the great move of going with Clang. And then we have the Microsoft compiler. So so what both are supporting is something we can support. So then I will look at it, and then I will send an email to my team saying, okay, we can use this on this and this in these conditions. So for example, we're not using the debug iterators from Microsoft, but I made my own actually in our container. And so what I did is I made a container, an iterator that is only movable. So that way I could use the last alive one and use its scope to make the container read-only while the iterator is existing by just incrementing an atomic count inside the container. So that's an example I have really quickly in my mind. But yeah, otherwise, yeah, I cannot think of other features, but yeah, we're using a few features on C++11. Cool, thank you for coming.